Okay, so this will just be a little quick overview of the 3D vectors, and then I'm also going to go through the problems on the worksheet that I asked you to do in case some things aren't clear. The answers are posted, but again, I'll go through things in case you need it. I guess the first thing is I'm going to show this picture here. This shows a 3D vector, and we see the vector here is the vector A. Put a little harpoon over it. And here, this is just a diagram showing it in component form. So if you can envision this being in the 3D box here, this vector, in order to get there, I have to take this many steps in the x direction. They're going this way. This many steps in the y direction. And then this many steps in the z direction to go there. And that would be the component form of that vector. The other thing to note here is this diagram shows unit vectors. I didn't really have a chance to talk about this in class, but the unit vectors I, j, and k also have a meaning in 3D. And it's kind of the same thing. The vector I is going to be a unit vector 1 in the x direction. So that's going to be 1, 0. But now we're just going to add the extra 0 in that component. So this is just, again, 1 pointing down the positive x direction. J is going to also be a unit vector. That's going to be going 1 in the y direction. That's the red one here. And then k, now that's the new unit vector. Hopefully by association you understand that the k is going to be a vector pointing straight up in the z direction. And so now we can write any vector as the sum of I, j's, and k's, just kind of like what's shown here in this diagram. Okay, so we move on to the worksheet here. We have two vectors, v, which is 1, 2, 3, and u, which is -4, 0, 2. So the first thing I've done here is I've rigged up the graphing program to try and graph this vector. So the first vector I'm going to graph is vector v, which is 1, 2, 3. And if I spin this around, you can kind of see what's going on here. If I look down on it, you can see that I'm going 1 in the x direction, and then 2 in the y direction. And then if I look up at it this way, you can see that I'm going 3 up in the z direction. So that's what that vector looks like. That's what 1, 2, 3 would look like. And then if I'm going to graph the other one, -4, 0, 2, see if I can get this to work here. That's the other one. So if I look, you can see here, since it's -4, I'm going the opposite direction in the x. That's why it's kind of spinning off to the back here. And then 0 in the y direction. So I'm staying, I don't move any in that y direction, and then 2 up in the z-axis. And so you can see kind of here, if I try to hold it there, I'm going up 2. So that's what those two vectors look like. If I draw them together at the same time, hopefully this will work. These are the two vectors that we're working with for this entire problem, and visualizing can sometimes really help see what's going on here. So we're going to do a bunch of things with these two vectors, like add them, find angles between them, and such. So, but here, if I hold them like this, you got a good sense for how they're oriented. Okay, the first question here is just to write these things in standard unit vector form. So this is really just another way of writing these in component form. So the first one's going to be vector v, and then here it's just going to be 1, I have 1i plus 2j, put little hats over these i's to indicate that they're vectors, plus 3k. Which I don't have to put I don't really need to put that 1 in front of the I, so I could just say it's I plus 2j plus 3k. And again, if I want to put some sort of marking above the I, j's, and k's to indicate that they're vectors, that wouldn't be the worst idea. And then the u, in standard unit vector form is just going to be -4 in the I direction plus 0 j's plus 2 k's. And again, I don't actually need to write that, so I could just write this as -4 I plus 2k. Now b here, recall that these absolute value signs around a vector just mean find its length. So these are the two numbers in quotes that we always talk about that are in a direction. We just need to find the length. And it's a straightforward application of I'll call it the 3D Pythagorean theorem. So the length of the vector, so applying the 3D Pythagorean theorem is just going to be the length of v is going to be the square root of each of those components squared. So 1 squared plus 2 squared plus 3 squared. So it's the component squared added together, and that's where it's like the 3D Pythagorean theorem. And we finish that off, we add that up, we see it's root 14, which is not simplifiable. And we do the same thing for the vector u. To find how long it is, we apply the 3D Pythagorean theorem. We're going -4 units in the x direction, square that, plus 0 units in the y direction, square that, plus 2 units in the z direction, square that, and that's going to be square root of 20, which is also the same thing as 2 root 5. For C here, we're just trying to find the sum of the two vectors, and recall that what would be going on, if I flip back to the pictures, we'd be putting these two vectors head to tail and finding and then drawing the vector from the starting point of one to the end point of the other. Can't really do that in this tool. But when we have the vectors in component form, remember adding them is as simple as just adding the components. So if we have v is 1, 2, 3, and u is the vector -4, 0, 2, we just add those vector components. We'll get -3, 2, and 5 as the vector sum. And we could go ahead and draw that if we wanted to. You would just go -3 in the x direction, 2 over in y, and then 5 up, and draw that vector from the origin. All right, so number D, or letter D, we're trying to find 3v minus u. And recall that this 3 here is scalar multiplication, so we're essentially taking v and stretching it by a factor of 3 and then taking away u. So the first thing to do here would be to actually find 3v. So if v is 1, 2, 3, 3v is just going to be 3, 6, 9. And then we know the vector u is -4, 0, 2. And then we subtract components when we're doing vector subtraction. So 3v minus u is going to be that 3 minus a -4, which would be 7. 6 minus 0 is 6. And then 9 minus 2 is 7. So that would be the component form of that vector. So dot products also work in 3D just like they do in 2D. So if I have the vector v, that's 1, 2, 3 again. And the vector u is going to be the same vector, -4, 0, 2. To find the dot product, we want to multiply the pieces that are in the same direction. So the x components are in the same direction, so we're going to multiply those. 1 times -4. The y components are in the same direction, so we're going to multiply those, 2 times 0. And then the z components are also in the same direction. Now that's the new piece, 3 times 2. And if you recall, we add those together to get the dot product. So that's u dot v. And that's going to equal -4 plus 0 plus 6. And we're going to get +2. And recall that the fact that this number is positive is going to tell us that there's an acute angle between the vectors. And if we go back to this little diagram here, it looks maybe close to 90, but it certainly doesn't look obtuse. So that dot product is certainly telling us what we expected to see based on this graph of those two vectors next to each other. And remember, we're putting them tail to tail. Sorry that this doesn't show any arrows on the vectors, because this is not really a vector graphing tool. Okay, for f here, we want to find the measure of the angle between the two vectors, and I'm just going to kind of draw two vectors to kind of get a sense for what we're trying to do. Remember, we put them tail to tail. It's like putting them on the clock, and we're basically trying to find theta, which is the angle between them. And this would be v, and this would be u. And recall that the dot product of two vectors, we know how to do it one way up here, but it's the first number times the second number, taking into account the relative direction. So we multiply them by the cosine of the angle between them. And that shows us the piece that's in the same direction. So if we solve that for cosine theta, we'll get u dot v over magnitude u magnitude v. Now, well, we have all these pieces from prior problems here. The dot product up on the prior problem is just 2. We know the length of u, which is the square root of 14. And we know the length of v, which is, the length of v is the square root of 14. The length of u is the square root of 20. And that would be 2 times the square root of 280 would be 2 divided by the square root of 280, cosine of theta. And then if you just do cosine inverse of that thing, you'll get 83.1 degrees is the angle between them. And again, if we go back and take a look at these, like I said, it did almost look like a right angle, so 83.1 certainly sounds like a reasonable calculation based on the picture we have here in the 3D tool. Okay, G is next. Find any non-zero vector that is parallel to V. Well, remember, parallel just means that two vectors are parallel if they're scalar multiples of one another. So if V equals 1, 2, 3, I can just pick any scalar multiple, k times the vector V here. If I want to pick, say, k equals 2, stretch it by a factor of 2, I'm going to have 2, 4, 6, and that would be 1. If I want to pick one in the opposite direction, I can pick a negative scalar, like k equals negative 1/2. That's going to stretch it by a factor of 0.5, so shrink it in half, and then turn it in the other direction. So I would just multiply all the components by negative 1/2, and I'd get negative 1/2, negative 1, negative 3/2. So there's all kinds of answers. There's obviously infinite number of answers you could pick here, but here's 2 examples. All right, for H, we want to find any non-zero vector that's perpendicular to V. Remember, two vectors are perpendicular if they share no components in common. In other words, the dot product is 0. So I'm going to say, let's call the vector we're looking for W, and let's say its components are x, y, and z. That means we want the dot product of these two vectors to be 0. So vector V, again, is 1, 2, 3. So the dot product of these two vectors here is just going to be 1 times x plus 2 times y plus 3 times z equals 0. And we just have to find some set of x, y, and z such that this is true. And you can pick anything you really want. You just have to, if I pick x as 1 and y as 1, I just have to then pick z so that this is equal to 0. So 1 times 1 plus 2 times 1 plus 3z equals 0. I'm just putting in the 1 and 1 that I chose at random. So 1 plus 3, 3 plus 3z equals 0, 3z equals negative 3, so z equals negative 1. And so that is one vector that would be perpendicular. We could go ahead and check it by doing the dot product back again. 1 times 1 plus 2 times 1 plus 3 times negative 1, in fact, does equal 0. And so, anything you find here is going to be some scalar multiple of this, because as long as whatever you find is parallel to this thing, it will be perpendicular. So you can check your answer. If you had something like 2, 2, negative 2, that would be fine. I here is just a unit vector of length 1. Find the unit vector which is in the same direction as u. So u here equals negative 4, 0, 2. I'm just going to draw it. I know this is not in 3D, but if I draw a vector u, and we know its length is square root of 20. That's what the magnitude of u is. We know that from a prior problem, which is somewhere between, 4 and 5. So a unit vector in the same direction would be something like this, but we want its length to be 1. So we want it to be essentially a scalar multiple of this vector here, but shrink down from a size of square root of 20 down to a size of 1. It's like if we wanted to shrink u down from, say, 5 feet tall to 1 foot tall, we'd multiply your height by 1/5. which is 1 divided by your height. Kind of the same thing here. We want to multiply this long vector by its 1 divided by its length. So that's all we're going to do here. The unit vector in that direction is, see what we call it. We'll call it W. It's just going to be 1 divided by 20, shrinking the original vector down. And then we could leave it like that, or we could multiply the component. We could multiply the scalar through. 0 and then 2 over root 20. And then you could continue to simplify radicals or whatever. But this is basically the answer. So this is the unit vector. This is a W. We're calling it W here. It's a unit vector because it's length 1. So all we did was take our original vector and multiply it by a shrink factor to get it to a length of 1. And then J here, well, I showed you this in the 3D program, but if you wanted to graph it, I'll just graph 1 here in the interest of time. The first thing you would do is when we talked about graphing points is you're going to graph the z-axis pointing up, the y-axis pointing across, and then an x-axis coming out at you. And then if we wanted to graph the vector v, which is 1, 2, 3, we really could start anywhere and step 1 unit in the x direction, step 2 units in y, and then step 3 units in the z direction. I think that's easiest if we start at the origin. You don't have to, though. And then we'd go 1 unit in the x direction. We'd step 2 units in the y direction. So now we're standing here on the floor. And then we're going to go 3 units up. 1, 2, 3. It's about that long, so we have to draw a spot about that long here. And that would be the end of that vector. So this is going to be really, these are hard to draw. But if I drew this in green here, that's kind of what we're doing here. That's a vector starting from the origin and coming out to this point. It's the diagonal of this box. I could finish drawing the box in using that parallelogram method that I took a picture of actually and actually posted that on Cluster. So it's the diagonal of this box here that I've just sketched. It has a 2 on that side, 1 unit on this side, and it's 3 high. And you can try it on your own for the other vector or check the answer key. And then for stretching your thinking here, I'm not going to cover that here in this video. You can check the answer key.